Hi, welcome to my clips on the analysis of statically determinate frame. The frame shown here is a steel frame. This steel frame is fabricated by connecting the beam to the column with the rigid joists. And this frame also has support. One can be pin, another one can be roller and pin. If one is pin and another is roller, this frame is called statically determinate. Can you draw the model of this frame and apply the force into this frame? Yeah, usually if this is a pin, you just make this is like a pin, and then you attach this pin into the support. Okay, and then this for statically determinate frame, you model this one as the roller. Okay, and support to the floor here. And for this column, okay, it can be up like this. And along this, you can draw the lines of the horizontal line. And then on this, you may draw the column. And since this is the rigid joist, okay, you may put some fixed rigid connection into here, and also needs to be here. Okay, and this frame may subjected to what? This frame may subjected to uniformly distributed load. Due to what? Due to the weight of the beam itself. And then following this, you draw the weight here, and then it's going to be the model that can use to analyze the frame. And if the weight of here is maybe a lot, you may put some more rod over here. And sorry for this, you just put the line along here. So this is the model of the frame. When you draw it, this line gonna represent the centroid of this beam, this column, and centroid of the beam is going to be the straight line. And next, another rigid frame. This rigid frame, if you take a look, the support here can be the pin support, okay, and also over here can be the pin support. And what happened is the weight of this small beam can transfer to what? To this beam. So this one going to have the reaction here, and also this one is going to have the reaction here, and the reaction here going to put to the girder. Sorry, let me put another color, so it's going to put it's better. So take this one out, and then let you select the pin with another color. Okay, let's see this one. So the selection here will apply into this beam, also will apply into this beam. And this beam also subjected to what? This beam may be also subjected to its uniformly distributed load along its length, and this one also subjected to uniformly distributed load along its length. And then this uniformly distributed load gonna be the reaction here, support by the reaction here, and also support by the reaction here. And by the third law of Newton, okay, the reaction here may apply again to the beam of the frame. Okay, and also this frame have its own weight. So this frame gonna have what? It's gonna have the uniformly distributed load along its length, okay, like this. And you can see the model of analysis of this frame can be created easily, and then all the forces will transfer to the to the to the support, to this support. Okay, and you may see this one, and since this support are pinned, this structure is statically indeterminate. Okay, unless you assume one of these supports is the roller. Again, you may see on this frame the load will transfer to the cross beam here to be the reaction. Okay, and that reaction is transferred to act on the girder. Okay, and the girder have its own weight. They transfer all the forces into the reaction. Okay, the yellow one, and this reaction by third law of Newton change to the green force. And since the beam of the frame have its own weight, is also apply the force across the column and from the column to the support here. This is a kind of the model that we use to model the frame and for the analysis of the frame. Okay, and we come to a simple structure here. The frame here is assumed over here. Since the frame over here is a steel frame which have the column here and the beam here, and the F is the free end, so the support E must be fixed support. Okay, under the action of the force, we can analyze it first by drawing the free body diagram of the frame, and then we have what? We change the fixed support into the reaction, and at the support here, they are supposed to have 3 reactions to make the frame be in equilibrium. Summation of f sub x equal to 0, summation of f sub y equal to 0, and summation of the moment equal to 0. And then if you like to draw the shear diagram and moment diagram of the frame, after you know these forces, for example, this one gonna be summation of x sub x equal to 0. This one gonna be 0 kilonewton. And then if you do the summation of f sub y equal to 0, you will get what? This one going to be the vertical force going to be equal to 1,500. Again, by using this frame, if you take the moment about this point, you may see that the moment is going to be equal to what? Equal to 1,500, and it's going to time the distance between here and here, which is going to be what? 4, 5, and then this is going to be 6.5, and then the moment that we are looking for is going to be 6.5 and time 1,500. That is going to be the moment going to be 9,000. Okay, 700 and 50. Sorry, it's not kilonewton. It's 50 newton and meter. This is going to be 0 newton. Okay, that's going to be the frame reaction. And then if you like to find the internal forces and internal moment to draw the shear diagram and moment diagram, you got to set, for example, this one gonna be the coordinate one. You may call this is like a x1 or y1, whatever you set, and this is going to be another x2. And then if you cut the beam, the frame into the given section, you can write the shear force in the function of x1 and x2, and also the bending moment at the function of x1 and x2. By that case, you will get the equation, and then you can draw the shear diagram and the moment diagram of the frame. Okay, by doing this, we go further. Most of the frame, let me know, the frame may have the column subjected to only axial load. That's we call the column. And if the frame subjected to both axial load and bending moment, we call this frame as the beam column. Okay, it is important because the combination of moment and P may produce the P delta effects. Okay, when you study the design of this member, Ajahn will tell you about the code that related only to the column and the code that related to the beam column, which is much more complicated, and therefore sometimes we need to draw the axial force diagram also to include the effect of this into our analysis results. Okay, and let us do some example so it will enhance your understanding on the drawing of the shear diagram and moment diagram. Let us consider the first example, which is the frame. This frame have the A as the pin and has the D support as the roller. So if that happen, we will have the force A sub x and force A sub y as A, and has the reaction force only in the vertical direction at the D. So we will have three unknown forces, which is equal to the three equation of equilibrium. So we can solve it. By doing that, we will draw the free body diagram, and then we will use the equation of equilibrium. By doing that, we take the frame out of the support, and then we put the reaction in according to the support. At D, we have D sub y because it is roller, and at A, we have the A sub y and A sub x because it is a pin. So we start by summation of what? Of f sub A equal to 0. And you can see if you put this, the A as the rotation, so the D sub A trying to rotate like this, counterclockwise. So if you say like that, you may say if that we will have the summation of the moment at A equal to 0. Okay, and then since this rotation is for the unknown, so we set the rotation like this is positive, and then our D sub y going to multiply by the moment arm between the D sub y and the rotation point. That is going to be 5. So we have over here is 5 D sub y, and then the uniformly distributed load here, they're gonna have the resultants of it in this direction, and you may see the volume of this is going to be what? The magnitude of this is going to be the total of 16. It's going to be 16 kilonewton per meter, and then it's going to time what? The length of it is 5 meter. So it's going to be what? 16 times 5. It's going to be 80, right? 80 Newton. And then this 80 Newton will have the line of action along here. And you may see that it's going to be half of the 2.5. And then it's going to produce the moment in this direction. So it's have minus, and then 80, and then it's gonna time what? Time 5 divided by 2. Okay. Next, we come to another load that acts on the column. On this, it's going to also have the resultant force here. This resultant force is going to be what? The area of the force is 12 times what? Times 4. That is going to be what? 48. The total here is going to be 48 kilonewton. And then the distance between this resultant force and the rotation point is going to be here. That is going to be what? That is going to be 2 meters. And also it's going to rotate like this. So it's going to be minus. And then 48. 48 what? 48 times 2. Okay. And you may set this equal to 0. And you do the computation, you will get the d sub y of 49.2. Okay, then you may have the summation of f sub y equal to 0 in order to determine the a sub y. The a sub y is upward. Let's take the upward as the positive. So we have the a sub y. And then the a sub y will plus both vertical plus 59.2. Okay, and the resultant force of 16 kilonewton per meter have the downward. Okay, have the downward. When it have the downward, so that is going to be minus of what? Minus of the 80. When it's minus of 80, it's going to be what? The a sub y gonna be 80 minus 59.2. So the a sub y, okay, that is gonna be 80, and then going to be minus 59.2. So you're going to get what? It's going to be 20. This one gonna be 20.8 kilo Newton. So you got the a sub y here for 20.8 kilonewton. And then the last one is here. Okay, we have the summation of f sub x, and then is equal to 0 to determine a sub x. So we put this direction as the positive. So our a sub x is positive. And then the uniformly distributed load on the segment AB gonna take the what? Opposite direction. So a sub x is going to be 48 kilonewton. Okay, and then all the forces are going to be in equilibrium. And after we determine the reaction, next step, we're going to separate the frame into 3 parts. Okay, to 3 parts, 1 part, 2 part, and 3 part. And we put the reaction that we have into the support at A and at D. Now, the problem is, what is going to be the shear force and going to be the bending moment acting on the end of this member? When you cut this, don't forget about the joint here, B, and joint here, C. Okay, because it's part of the structural member. And then what happened is, if you consider the column CD, you may see that this column has what? Has only the vertical force. So there is no horizontal for the shear here. Shear here is supposed to be 0 because there is no horizontal force. And also the moment here. The moment here also need to be 0 because there is only the axial force along the member. So we have only the force here. So this is like say to be C sub y. And if you do the summation of f sub y equal to 0, you may see that your C sub y is downward. It's going to be positive. So C sub y is going to be 59.2 kilonewton. So you get this green, okay, in the same direction. And then this is 59.2. This 59.2 going to act. Okay, let me change this one a little bit to the green yellow. Oh, light green here. Yeah. And then the force over here, due to the third law of Newton, when this 59 is downward, so the force X over here must be upward. And due to the equilibrium of this point C, the force here must be downward with 59.2. And again, due to the third law of Newton, the force here also must be vertical. And then for summation of f sub y equal to 0, you may see this one is going to be 59.2. Okay, now let us consider the NB. Okay, the B is going to be the rigid joint. So if this happen, okay, we going to have the shear force here, and the shear force going to be like this. Okay, this is going to be V sub B. Okay, and we also have the vertical force. Sure, we're going to have vertical force, and we also need to have the moment. And if you do the summation of x sub x equal to 0, this horizontal force is going to be 0, since there is no horizontal force here. Okay, and by doing this, if you summation of f sub y equal to 0, by doing this, you will get what? The V sub B is upward. So the upward is going to be positive. You're going to have V sub B. Okay, your V sub B is going to be upward. And then 59.2 also plus, okay, 59.2. And then if you remember the resultant force of this uniformly distributed load, if you remember it, what is the value of this? The value of this is going to be 16 times 5. So the value of this is going to be 80 kilonewton. And this is a downward, so minus, this is minus 80, and then equal to 0. So all the vertical force is written here, and then you're going to have V sub B equal to what? 20.8 kilonewton, and this is going to be 20.8, okay, 8 kilonewton. And then if you sum the summation of the moment here, you may have this one for the M sub B. Let's see, if you do the summation of moment about B, and then equal to 0, you may get M sub B. Let M sub B rotate like this. Okay, M sub B rotates like this. Okay, let me have this one already is 20.8, and oh, sorry, this is in opposite direction. Let me try to erase this a little bit. This is not good. Okay, this is not good. Not good. Okay, this is going to be m sub b. Let's say, let's put this in this way. This is going to be m sub b. M sub b. So we have summation of moment about b. So the counterclockwise is going to be plus, and then we have what? We have m sub b equal to 59.2 times this length. This is going to be 5, so it's going to be m sub b. M sub b. And then 59.2 is in opposite direction, minus 59.2 and times the length of 5. And then we have the resultant force of 80 kilonewton, which act at the half of 5 meters. So this is going to be in this direction. This is going to be in this direction. So this is going to be plus what? Plus 80. 80. And then 80 times what? 80 going to times 2.5. 2.5. Okay, and then make it equal to 0. And then you put into your calculator minus 59.2 times 5, and then this is minus, okay, 80, and then you get, this is not a good lighting, okay, this is better, and this 80 is not good, so make it a good better than here. Let me do it again. By using mouse, it's pretty hard to write it in a proper beautiful manner. Okay, and then we have this. Then we do the calculation. The m sub b gonna be 96. Let's put other thing in the calculator and check it out before you go further. And then the obtained shear and moment gonna be what? The moment here gonna transfer to this one by the third law of Newton. The upward shear gonna be downward shear. Okay, and the downward shear gonna be this axial force, and this one gonna be 20.8 kilonewton, transferring from this blue to this red up this one, and then is apply vertically. Sorry, apply vertically here. So it's going to be downward, okay, downward here, okay, downward here, and then the moment, this clockwise be this counterclockwise, and then for the equilibrium there is a moment here in which is going to be the moment at here. So we have the moment here, and then if you do the summation, you may see the summation of the force in the vertical direction is equal to 0. And then if you do the summation of f sub x sub x equal to 0, you may have this force, which is, if you remember, is 48, okay, kilonewton, is going to balance by this force. Okay, this is going to be correct. If you do the summation of f sub y equal to 0, you may get 20.8 and 20.8. And if you like to do summation of the moment about what? If you like, about b, and if it's equal to 0, if you have this one is 96, rotate this one, is plus, is going to be 96. And if you do this, you have what? You have this one going to rotate in the same manner of this green moment. So it's going to be 48 times what? 48 times 2. This is plus. Okay, plus. It's going to be 48. And then times 2. And then what? You have this 48. Okay, this 48 going to be rotated in this way. So it's minus. This is another 48. And then it's times 4. Okay. And you may see this is going to be equal to 0. So this equation is also correct. So everything is in equilibrium. If everything is in equilibrium, now we draw the shear diagram and moment diagram. We first take the column AB as our first piece. When you draw the shear diagram of the column, it's going to be from the A to the B. That means what? That means you got to put the x equal to 0 here, and then up here is going to be 4 meter. Here is going to be 4 meter, and it starts from the bottom to the top. So when you move to this, you got what? You got the horizontal force. So this one is going to be positive 48. And then you come over here, the slope dv by dx is going to be minus 12. So by doing this, the slope here is going to be equal to minus 12. Okay, that's very bad drawing. Sorry on that. Okay, let me take this one out so we make it a lot better. So this one going to be minus and also 12. And then what is going to be here? Okay, if you take a look here, there is no shear, so this one supposed to be 0. Okay, if you don't believe it, you may have the shear here, the shear at B, V sub B, and then minus what? Minus 48, minus the 48, and it's going to be equal to what? Equal to minus the area here. The area here is going to be 12 times 4, and then you can see clearly V sub B is equal to 0 kilonewton. Okay, that's proof. And then for the moment, there is no moment at A, so the moment at A start here is going to be 0, and this is going to be 4 meter. Okay, and the moment here start by 0. However, we have the shear here, so when it start here, the dv by dx, the slope here, gonna have some value. Okay, this gonna have the slope here, the slope here. Just start the slope here. The slope here must be equal to this 48 because dm by dx equal to v. Okay, up until this we have the s slope equal to 48. Okay, it's put here, and then also the shear change from 48 to 0. So that means at the end of this is going to be slope of 0. So over here is going to have slope of 0. So we have here s equal to 0. And what the value of the moment here? And if you can predict, this is going to be 96. But if you don't believe it, we can do it m sub b minus m sub b is here, minus the moment here of 0, and then it's going to be equal to the area, sorry, the area, oops, that's misdrawing, the area of, let's put this way, it's going to be better highlight, okay, the area of this. So the area of this is going to be 1/2 of what? 1/2 of 48. 1/2 of 48 equal to 1/2 of 48, and then time what? Time the length of 4, and then you may see m sub b gonna be what? Gonna be 48 times 4 divided by 2. That's going to be 96 kilonewton and meter. Okay, you get this already. Next, take a look at the beam BC. Take a look at the beam BC. From this, we have slope of this of 48. This is slope equal to 0, and then you take this of 96. Next, take a look at the beam BC. For the beam BC, again, we draw the shear diagram, and then we start with the B. The B has a shear of 20.8, okay, up to this one, and then you move up, you get the distributed force of 16, so dV by dx, which is the slope, is going to be minus 16. Okay, and then this is going to be moved downward like this, and then the shear here, you may not believe it, it's going to be V sub C is equal to V sub C. V sub C is here, oh, not equal to, V sub C minus takes minus of what? Minus of 20.8, minus of 20.8. This is going to be 20.8, and then it's going to be equal to the minus of the area here. If you see, this is going to be 16 times 5, which know to be 80, so your V sub C is going to be minus 80, and then you plus 20.8, and then you get the 15 minus 59.2 here. And since this is 59.2, you have what? You have the upward. So this one gonna cross your shear diagram here. Okay. And the distance here, can you find it? Okay, the distance here maybe, let's say it's going to be 20.8 divided by what? Divided by x. That is going to be 20.8, and then you divide it by x, so it's going to be what? It's going to be the slope 16. So if you move x up, this one going to be 20.8, and then it's going to divide it by 16, and then you're going to get this of 1.3 meter. Okay, you get everything. That is going to be your shear diagram. How about the moment diagram? And then you come to this moment. The moment that's rotated clockwise is positive, so this is going to be up for 96 kilonewton meter, and then this is going to be the slope dm by dx equal to v. So the slope here, the slope at this point, okay, you may mark this one is s equal to 20.8. This one is positive, right? Okay, it's positive. And then over here the shear is 0, so the s at some point of this gonna be 0. And what the value of moment here? Value of moment here must be m, and then minus what? Minus 96. when n minus 96 is going to equal to the area here. Okay, the area here is what? The area is 1/2 of 1.3, and then it's going to time what? 20.8. Okay, 20.8. So you will get the value here, or y, by what? By m. Then it's going to be equal to minus 96 is going to be plus 96 here, and then it's going to plus what? It's not what? This is going to be 10.4. 20.8 divided by 2 is 10.4, and time 1.3 is 13.52. This one is going to be 13.52. Okay, and then you plus 96, it's going to be 109.52. So the result of this is going to be 109.52. Okay, over here show only 149.5. okay, kilo Newton meter. That is the moment here, and the slope here is also must be 0, and you have the curve here. And finally, since this C section have no moment, so for sure this is going to be 0, and then you got to provide the slope as this important point. The slope here is going to be what? The slope here is going to be equal to shear, and since shear is minus 59, so slope here is going to be minus 59.2. You may see every point have their own reason, what the value they are. Okay, and finally we have the column ACD, and this column have only axial force, so the shear is 0 and the moment is 0. And that is for the first example for drawing the shear diagram and the moment diagram of the frame. And then you combine the whole picture of this, and when you combine it, you must provide the value of some important point, and then you put the slope. Okay, the slope for here is going to be what? My mouse is so sleepy, sorry. The slope here is what? The slope here is gonna be, if you may remember, gonna be what? Sorry, it's gonna be minus 12. Okay, that's going to be minus 12. So the slope here, just put the slope to be your example, s equal to minus 12. Okay, and you may highlight to make it a little bit more understandable. Okay, this is highlight, and this is highlight, and to make this more clear, this highlight. Okay, and then you also has the slope of this also have the slope. Okay, have slope and have the slope. The slope of this is going to be minus 16 if you remember it, because the uniformly distributed load here is 16 kilonewton per meter, so this is going to be minus 16. Okay, and the column here is okay. And then again for this is going to have the slope of 20.8, and this is going to have slope of 0, and this is going to have a slope of 59.2. And if you may like, you may put this one, the slope here is okay, equal to 20.8 at 20.8, and this one s equal to 0, and this one s equal to 59. Sorry, that's it hard. I got to buy some pen for this. Okay, this is going to be minus 59.2. And then for the column, okay, we have what? We have the slope here. The slope here is going to be equal to this. This is 0, so slope here is 0, and slope here is what? Slope here is going to be 48. If you can, okay, you just say this S is going to be 48, okay, and this S is going to be 0, okay. And that is your your conclusion of the shear diagram and moment diagram. And then you get the maximum moment of 109.5 on the beam, and get the maximum shear of 48 kilonewton for the column there. Okay, that is the end of our first chapter. Sorry, our first example on the drawing of shear and moment diagram of the frame. Okay, this clip again will be the example of the analysis of statically determinate frame. And after we draw the free body diagram, we find the reactions, and then we will draw the shear diagram and bending moment diagram by using the graphical method. Coming into this frame, let's consider the support by this figure. This support is the roller, okay, due to the construction of this, and the support at A is going to be the fixed support, and what we have also is the joist here. This is the pinned joist, okay. When the joist like this, we're going to separate the beam, and then it's going to help us to analyze the structure. The fixed support has what? Has 3 unknown, and the roller supports have 1 unknown. That means what? We have unknown of 4, which is larger than the number of equilibrium. If we consider the whole structure, we cannot solve for the reaction of 4. And what we do again, since this connection is the hinge support, or is a kind of support that cannot take the moment. So when we separate the column AB to the beam BC, okay, again, this is going to be 4. We cannot solve it. We need to separate into beam and column. So when we separate this, what we have unknowns is 4, so will be here, and at the B we could have B sub X and B sub Y. Okay, the B sub X is the blue, and this is going to be B sub X, and the pink, and then the vertical is going to be B sub Y. Let's say it's B sub Y. And when you have this kind of connection force by the third law of Newton, you will have the blue in the vertical direction. You may notice this. What? This is the shear here can transfer the here directly, and also the normal force here will transfer to this directly. Or if you are so detailed in calculation, you may consider the joist here as the B joint, and then you may transfer the axial force here first, and then the shear here, okay, by the third law of Newton. This is to the left, this is to the right, this is up, this is down. You also get this axial force due to this shear force, and you will get this shear, okay, to be this shear. And you can see, you may do detailed calculation by putting the column, but you also can skip this and you can transfer it directly in the condition that there is no force and no moment acting at that joint. If there is moment or if there is force, we cannot transfer this directly. Okay, let us consider this. And then the force here can be separated into vertical. When it's separated into vertical, the 3 gonna times 100 and then divided by 5. And for the horizontal, this 4 will be divided by 5 and then times the 100. Okay, it's up to what you are going to project to. If you project vertical, you use the vertical divided by 5. If you project horizontal, you use the horizontal length divided by 5. And now, if you like, you may determine the forces. Okay, about here. By determining the forces, we start by taking the moment about B summation. Moment of B equal to 0. And then the C sub y gonna rotate like this. Have the clockwise, counterclockwise rotate is positive. So we have C sub y. Our C sub y gonna time what? Our C sub y gonna time the total of 6. Okay. And then the beam usually assume have very small depth, so the inclined force will produce very small moment and negligible. So it's only on the 60 times 5. This is going to be the 60 kilonewton. The 60 kilonewton gonna rotate what? Gonna rotate in the clockwise direction. So when this one rotate in clockwise direction, so it's in opposite to this. So it's going to be equal to what? 60. 60 is a force here, and it's going to time what? It's going to time 6. Okay, and then this is 60 times 6. So the C is, oh, what happened? No, this is not times 6. This is going to time 3. Oh man, what happened? This is going to time 3, not 6. Because the distance between the distance between the force and the B sub B is going to be here. That is going to be 3. Okay, and then the C sub y gonna equal to what? To 30. Okay, 30 kilonewton. And then you get the C sub y of 30 kilonewton. And then you get this, you go further to determine the force. What you can find? Summation of what? Of F sub y equal to 0. You can determine what? You can between B sub y. Okay, so this is up, is positive. Okay, so our B sub y is up 30 is up. Okay, all of them is going to be equal to the downward of 60. And then the B sub y is going to be 30, and it's understandable because the 60 kilonewton is at the middle of the beam, so it will transfer half to the left and transfer half to the right, so each of them get 60 kilonewton. And then the last one, use summation of f sub x equal to 0. That means at this time the b sub x over here is, let's say, is plus, so the b sub x is going to be what? The b sub x is going to be, this one is going to be 80. This is 80, so this is going to be 80 kilonewton, and you will get this is 80 kilonewton. Okay, and this is 30, this is 80, and 30 and 80 going to transfer to here. The 80 is here, is follow this, and also the 30 is here. And now the portion of this, the unknown, that's total of 5, now is reduced to only 3 unknown. Okay, and if you like, you may see summation of f sub y, and is equal to 0, and you may see what? See the positive is plus, up is plus, and then you get the a sub y, and then the a sub y gonna be equal to, easily equal to 30 kilonewton. So the a sub y is 30 kilonewton. Okay, the upward equal to the downward. Okay, and then if you do the f sub x, okay, this side, if you do the f sub x equal to 0, and then what you have is the a sub x, so you put this at the positive, and then your a sub x is what? A sub x point to the left, and the 80 point to the right, and also the resultant force here also point to the right, so it's going to be minus 80. Okay, and also minus what? Minus, let's take it out, glasses. Okay, let's put it in again. It's going to be minus of what? The next is going to be 5, and then times 4. Okay, and you're going to get this equal to 0, and then your a sub x is going to be 100, right? This is going to be 100 kilonewton. This 80, this is 100, and then the m sub a, then you determine the m sub a. You got to take the moment here, you got to summation of m sub a, and then equal to 0, and what you have is rotate like this is positive. Okay, so by doing this, the m sub a is in this direction, and it's going to opposite to this resultant force of 20 kilonewton. This is 20 kilonewton. 20 kilonewton gonna time what? Gonna time this distance, and this distance is 2 meters. So the m sub a is equal to, or if not equal to, okay, 20, and then it's gonna time 2, and then there is the 80 is going to rotate in this direction opposite to m sub a, so it's going to be equal to the 80 the 80. Oh, my hand is hard to control the mouse, so it's 80 times what? Time is 4. Okay, this is 4, and then this is going to be 330, this is going to be 40, so this is supposed to be 360 kilonewton meter. Okay, that is the moment m sub a. Okay, follow this. You have this 20 kilonewton. You have this for 100 kilonewton, and you have this for the 30, and m sub a. M sub a is 360, as we have before here. Okay, we start by drawing the shear diagram. The first one is the beam BC. For the beam BC, we may have this one as the horizontal, and you may have this 30. This is the pass 30, and then no uniformness here, so the S, the S here gonna be 0, so the S here gonna be 0, and then you arrive here, you're going to get the 60, so this is 30, so it's going to be downward with this, or the 60, so it's minus 60, and then it's plus with 30, and then you get the result of minus 30. Okay, and then no uniform distributed load. The S is equal to 0, and what we have is this one is constant, and then over here you get this one for the 30. So that is going to be the shape of the shear diagram. And then the moment diagram. Oh, I supposed to buy the pen, if I should be. This is the pen, and then we have this as the horizontal line, and then what we have is 0 moment here, and also 0 moment here due to no moment, and then this is the 30, so the slope here supposed to be S equal to 30, and it's going to be all 30, okay, until here, and the moment here is what? You don't know it. The moment m is here is going to be minus 0, and it's going to equal what? It's going to equal to the area of this, and the area of this is going to be 30 times 3, so this is going to be 30 and then times 3. So what we have is the m here is going to be 90 kilonewton and meter. So you have this here, and then the shear change from the plus 30 to minus 30. That means we will have the S here equal to minus 30. Okay, and then also the moment here is 0, so you just draw a line close to here. So this is going to be the triangle shape of the 90. Okay, and for the column you have this, and then you start with what? You start with the shear diagram. You draw this line. Okay, and line is not vertical. Let's take this one out, okay, let's take this. Okay, take this one out. Okay, you may draw like here, and then and you start to draw from 0 meter to here is 4 meter, and then we have what? We have the 100 Newton. So this one is up, and it's up for 100. Okay, this is up, and then it's up for 100 Newton, and then the slope here is going to be minus 5. So we have the slope along here is going to be minus 5. When slope minus 5, this one will have the straight line about here. It's really hard to draw this, so sorry for this. Let me erase all of this. Okay, and then just put the figure onto it, so it's going to be easier to do so. And takes it out. The mouse is not accurate to draw this picture here, so we have this. But it's going to be easier. Okay, the this one gonna what? Gonna have the value of what? 100. Okay, your life is 100, and then you get what? You get uniformly distributed load. So the S here along this line, or the S, or the S, or this S, or this S is going to be negative. It's going to be a negative of what? It's going to be the negative of, my mouse pad is bad. This is going to be a negative of minus, this is minus 5. Okay, and see, you have the 80 here, so this is going to move this. That mean the value of the shear here supposed to be 80, and if you guys don't believe that's one gonna be 80, guy can compute to check it easily. This is gonna be V sub B. Okay, this V sub B is minus what? This 100. Okay, and then it's going to be what? It's going to be equal to minus of the area here. The area here is going to be what? It's going to be 20, so it's going to be minus 20. And then if you move this one, the V sub B is going to be minus 20, and then it's going to plus 100, and then you get this for the 80. And when you get this for the 80, the pink force just close the loop. This. Okay, next we have the shear diagram like this. Why this is in this direction? Because the clockwise is positive, counterclockwise is negative, so the moment here is negative. And then what? And you get this 5 kilonewton meter, and the m by the x equal to slope, and slope is 5. Sorry, so it's 100. This is 100. The slope is going to be 100. So this one is equal to 100. So the slope will change until here, and see there is no moment here. So moment here is 0, and slope here is what? You got to put the slope here. The slope here is going to be 80. Okay, that is going to be the 80. So the shape of the shear diagram and moment diagram going to be like this. And finally, if you combine them, you got this. And don't forget what indicate the slope. This is gonna be 0. This is gonna be 0. Okay, and this is gonna be minus 5. Okay, and then put some remark on this. It's gonna help to indicate the slope clearer. So just mark this to highlight it, and this is 0, this is 0, this is 0, and this is 0. So it's going to be very clear how it's come. Okay, and also you have the slope here of 100, and slope here of 80, and then you have the slope here, and slope here of 30, and minus 30, minus 30, and minus 30. And if you can show your link, okay, you may see the 100, the shear gonna be the slope here, and also the shear gonna be the slope here. You can say is S equal to 80. Okay, this is S is going to be equal to 100. Okay, this is S is equal to 30. This is S is equal to 30. and this is S is going to equal to minus 30. Okay, that is the shear diagram and moment diagram. When you do the examination, you're supposed to put every important point with the slope and the related value. Okay, that is the end of the example.